QRS, and this is my talk for evaluating and improving static analysis tools via differential mutation analysis. This is joint work between myself and colleagues at Trail of Bits, Jocelyn Feist and Gustavo Grieco, and at UC Irvine, Iftikhar Ahmed and Iftikhar students Jiri Gesi, Mehran Medani, and Kihong Chen. So the problem that we're tackling here is evaluating static analysis tool. And actually one particular aspect of the problem, which is given a set of static analysis tools for a language, first of all, having some idea how much their results overlap. If one tool is clearly inferior in that true positives it reports are a subset of positives reported by another tool, and particularly a much smaller subset would be the really interesting case where you just don't want to bother with that tool, it's worse. And cases where you just have multiple tools and you want to see what one of them detects that another doesn't. That's interesting and probably a true positive. So static analysis, briefly, again, is analysis of code without running the code. So we're looking from source code for things that are potentially errors, that are problems. The core issue in static analysis is, in theory, you could find all potential bugs by pointing to the entire program and saying, hey, this line might have something wrong with it. Who knows? Hey, maybe there's something wrong here. That's pretty useless. Obviously, if you have a burglar alarm that continually goes off, it does not help you detect burglars. On the other hand, that problem, the one of false positives, is a problem. But of course, if you go too far in avoiding those, you have a burglar alarm that never goes off, reports no problems with any lines of code. It won't annoy you with irrelevancies, but it's also completely useless. So the sweet spot for static analysis is somewhere in between. A tool that says, here are some parts of your code. Those pieces of code are potentially buggy. Okay? They give you a warning that says, here's what's wrong with it. All right, easy to understand. So how do you compare these? Well, it's difficult. If you want to compare a bunch of tools, humans have to look at the warnings produced and determine if they're false positives, true positives, figure out the negative set, etc. So, and this limits how big a code base we can really try to compare tools across. A human just has to look at lots of stuff. So what we want is a way to take realistic code bases, generate realistic bugs that static analysis tools might be able to detect, and then use that to compare the tools. So our idea in this paper is to use mutation testing to do this. So traditionally, mutation testing takes a piece of code and injects small syntactic changes to induce bugs. We then run traditionally a dynamic test suite to see if that test suite can detect those bugs. And of course, because it's a dynamic test, it should be able to check lots of things. We really hope that it will detect most of the bugs, perhaps essentially all the bugs that aren't actually equivalent in a semantic sense. We have no such hope for static analysis. Obviously, static analysis tools cannot detect a large number of bugs because they have no static signature. They're wrong at runtime. They cause the program to, divide by 0 or not do what it ought to do according to some complex test suite. Static analysis tools aren't supposed to detect this kind of thing. That's fine. Our idea is we can still use mutation analysis to generate lots of mutants of a program, and then we run static analysis tools on the set of mutants, and we compare how well each static analysis tool does. So the idea is if I have a program and say 100 mutants of that program, and one static analysis tool detects 20 of those mutants, that's fantastically good. 20% of the changes we made, the tool was somehow able to distinguish from the original code that it didn't find any problems with. That's sort of the base assumption here. The original code is clean. The tool doesn't find a problem. I'll explain in a moment how we get around this rather, strict assumption. But the assumption is let's start with code that two tools find clean, okay? So to make this concrete, let's take an example. Let's take a tiny Python program. Actually, let's give you some white space after the end so that you can tell where that ends. Okay, we have a tiny program that checks if data is sorted. It grabs the last element of data And then for an element in the data, if E is less than the last element, so we went down, we didn't monotonically stay the same or increase, then we return false. And then it assigns last to the last element. And then it returns true if it gets through all the data without this happening. Okay, simple enough. So we use a mutation tool, the universal mutator, which you can find a reference to in the paper, to mutate that program. So it generates a lot of variants. There are 19 that are valid compiling Python, 18 that don't really compile. They sort of break the code in a way that just, it's no longer good Python. And there's 5 that are redundant. They're semantically equivalent. They have the same Python bytecode as another mutant. They're not interesting. So we have 19 variations here that a static analysis tool could, in theory, detect. We want to look for which tools will detect those problems. So let's run PyFlakes, a popular Python mutation analysis tool, on the original program. And let's run PyLint. Okay, it's slower, but they both say, there's nothing wrong here. This is good code. All right. But we have all those mutants. We don't just have the original program, we have all those mutants. So let's analyze mutants. And our analysis, what we're going to do is run PyFlakes on those mutants. And we want to see how many mutants detected. Now, I think most of them won't be. Most bugs we can induce in this code are not statically clear. There's no specification here that tells PyFlakes or any static analysis tool, hey, I want this to tell if the data is sorted. It doesn't know that. It just knows things that are obviously, egregiously, statically wrong. Like this can't be right, or this is clearly a unsettling pattern in your code. So let's try that. Analyze mutants. Got to tell it what file. Sorry. Toy.py. We're mutating toy.py. So it runs through. It detected one mutant. It killed about 5% of the mutants. Okay, so it killed one mutant out of all those. If we cat killed.txt, there's one mutant. So let's copy that to pyflakes killed.txt. So we killed one mutant. That's not great. Okay. Now let's do PyLint. Okay. Let's see if PyLint does better. So again, these are very popular Python static analysis tools. They're widely used. You'll find them in lots of people's continuous integration on serious Python projects. It's slower. PyLint is a slower tool. I have configured PyLint here not to signal like white space, purely like look and feel type bugs. PyLint looks for lots of those. The mutation tool changes the formatting in ways that don't cause any semantic change, but that PyLint's like, I don't like the way you have your commas here and stuff. So we've ignored all that, okay? That's not part of what we're doing. So let's see. It didn't kill any mutants. So let's look at the one mutant that was killed. Okay, so let's diff with the original. So we changed assigning last to data sub 0 for just a pass. We essentially deleted that statement. And if we run pyflakes on that, it says there's an undefined name last. The local variable last is assigned to but never used. That's a little misleading because I don't know why it thinks that like that's assigned to but never used, because actually it is used here and E is less than last. But the undefined name is actually a serious problem. And PyLint just thinks that file is fine. So this is a hole in PyLint. PyLint, for whatever reason, this is a bug that is is clear, pretty obvious. This code is bad. PyLint doesn't detect it. Now, I'm not saying PyLint is worse than PyFlakes. This is just an example of something. It's a toy program, a small example. You wouldn't use this as a useful data set for comparing the two tools. But you have a technique now by which you could compare two tools, okay? So there's a lot of details here. So one question is, what if, unlike this, both tools signaled, bugs with the original code? So what we did is we considered that you kill a mutant, you detect the mutant just as in mutation testing, if the number of warnings you issue for that program increases with the mutant. So you add a new warning when we mutate the code. The code is more wrong according to the static analysis tool. This is a conservative rule. It will miss cases where, say, a mutation eliminates an old warning and creates a new warning. We just count warnings. So we're only rewarding a tool if it generates a new warning. This is a limit, but as we look in our data, it doesn't seem to affect the results. They're the same over code that's clean and not clean. Clean being if the mutation tool is working on code where the original static analysis tool flags nothing in the code. So skipping over this, what you can get out of this for tools, here's an example of what you want. Overlap between tools. So we have tool A, tool B, and tool C. All of our results in this paper are comparisons of 3 popular or at least well-known tools. And here we have tool A looks good. Tool A kills more mutants than the other tools, and it has a pretty decent overlap. Tool B also does well. Tool C doesn't have that many unique mutants it kills. Tool A is very much worth running on your code. Tool B is probably worth running on your code because it seems to detect quite a bit of stuff independently of Tool A, different things. Tool C doesn't do that well. Let's look at some results for real stuff. So here's 3 popular tools for smart contracts: Slither, Smart Check, and Securify. Slither has the same pattern. Those A, B, and C here, in fact, in the intro, are Slither, Smart Check, and Securify on a smaller data set. So Slither detects a lot of unique mutants. Smart Check detects quite a few, and Securify detects a smaller number. It's not too bad. If you look at the results, Slither tends to detect about 10% of mutants. It gets up to 11% over code that's clean, where there's no problem. Smart Check does 5%, goes down to 3% with clean. Securify is 3, 0% on clean. And then there's something called the mutant ratio, where we take a ratio between the number of findings overall that the tool produces on code and the mutants that it detects. So we don't know if findings originally are true positives or false positives. A tool could be a bad tool that also flags a lot of totally fine code as wrong, okay? We are making the assumption that mutated code that a static analysis tool can detect is wrong. There aren't very many reasons a mutant could be detected that aren't, distinguished from the original correct or more correct code. There aren't very many such reasons that don't flag a real problem. So mutants are very likely, if flagged, to be true positives, actual problems with the code. If a tool is really verbose, says lots of things are wrong with the code, and these are not just stylistic problems, they're claimed actual bugs, but it's very bad at detecting mutants, that probably means it's false positive prone, but it's not even very good at finding real bugs. So the mutant ratios here, Slither does very well, Smart Check does pretty well, and then Securify does terrible. Securify also took a long time to run. It's not really a tool that anyone uses much anymore. Smart Check's also somewhat deprecated. Slither has become sort of the standard in this area of smart contract analysis. Now looking also, we have results for... So we also use this to find some things, though, to add to Slither. Slither has a really good engine behind it, and we were able to enhance Slither so that it detects more things, and these have actually resulted in detection of some real bugs and real systems in security audits. So here we look at Pylint and PyFlakes. Pylint does really well, but Pylint's also really verbose. PyFlakes doesn't detect as many mutants uniquely. There's a lot of overlap between them, but it's really good at being quiet, but the things that it tells you are real. PyChecker doesn't do terribly well. It's an older, more deprecated tool. For Java, our result was, let's find it. Sorry, having trouble. Here we are. So infer really isn't meant for this problem, but it's a good baseline to show that if a tool does something but it isn't really good at this problem. You'll see that. That's very clear here. Infer is the one tool that just did extremely poorly in our results and didn't really kill any unique mutants other than some very odd ones. Spot bugs and PMDs seem to be independent, but both find interesting things. Spot bugs has a better ratio, though again, it detects fewer things absolutely. That's good to know. You should probably run spot bugs and PMD. You should probably run PyFix and PyLint if you care about analyzing Python code. Slither is really the only game in town now, as far as I know, on smart contract analysis, purely static analysis. But it's good to know that it was a good tool as part of why it triumphed. It was genuinely probably better, and we managed to incorporate some of the things that SmartCheck and Securify did that it didn't do at the time into it using this approach. For more details, you really should read the paper. It's not a hard paper to read. I think I've conveyed the concept, and of course I'll be glad to take your questions here during the talk. And how do I stop this?